Hello everyone, I am Dr. Mahendar, Associate Professor in the Department of Mathematics at B.V. Raj Institute of Technology, Narsapur. So welcome to Mathematics Orientation. In this video, we will focus on one of the important prerequisites, function and visualization. So before going to this concept, so we have some connection of this concept of function with the real life. So where do you come across this? Can you think it? Where do you observe the concept of function in the real life? So I quote one two examples. So recently I visited IIT Madras. So lunchtime I have seen one machine there, that is the vending machine kiosk. So the person they scanned and selected the item, it is displayed that one. So the moment if you give the input, they are displaying the output. Not only that, you can see in our campus daffodils too, we have the kiosk machine is there. If you scan and select the item, that will give the required snacks or tiffin. Even if you think it for ATM also, if you put inside this ATM and enter the pin, so based on the availability, that will display the cash. So all this case, what do you observe that? So we are giving the input, then the process, that will give the output. So this we have the connection with the concept of function. So with this small motivation, I will go to the, we will define mathematically what is a function first, then after that visualize that one. What is the function? How to define mathematically function? So define mathematically function, what we require that one. So what we need to define the function? Just think it. Yeah, we require relation. In order to define function, we need relation. What is the relation? What is the relation? For defining the function, we need relation. We need relation. What is the relation? How to define relation? For defining the relation, what we require? We require set. So relation is, if A and B are any two sets, then subset of A cross B is called relation from A to B. Suppose if A and B are any two sets, then subset of A cross B is called relation from A to B. Here R is subset of A cross B, here therefore R is called relation from A to B. So we know what is meant by A cross B. A cross B is called Cartesian product of two sets. This is Cartesian product of Cartesian product. How to define the Cartesian product? If A and B are any two sets, the Cartesian product of A comma B is represented by A cross B, defined as AB, this A coming from A and B coming from B. B coming from B. This is the Cartesian product. If you have the sets, then we can construct the A cross B. So once we have the A cross B, so any subset of A cross B is called relation. Any subset of A cross B called relation. We know subset. When we say that one set is subset of another set, suppose when we say that a set A is subset of B, if every element of A is element of B, then we can say that A is subset of B. And suppose instead of B, if you take A, for example, if I define A cross A, so here this is R is called what here? Here R is called relation from A to B. A to B. Here if R is subset of A cross B, is called relation from A to B. Suppose R is subset of A cross A, R is subset of A cross A, then R is called relation on the set. Suppose we have only one set instead of two sets. If I have taken one set, if you construct A cross A, the any subset of A cross A is called relation on A. Then this is called, R is called relation on set A. On set A. And we are familiar in the lower classes, if any relation on a set satisfying the three relations, the namely reflexive, symmetric and transitive, that relation is called equivalence relation. That relation is called equivalence relation. You heard this, equivalence relation. What is the significance of this equivalence relation? Anyone can think it. What is the purpose of defining equivalence relation? So once we have the relation on a set, the relation satisfying these three conditions, the reflexive, symmetric and transitive, that relation is called equivalence relation. What is the significance of equivalence relation? So do you observe anyway this concept? What is the purpose of this defining the equivalence relation? For better understanding, I will give one example. Suppose if you go and see some shoe showrooms. So there they will display in glass, they will display some of the models. Maybe I think they will display some 20 or 25 only. So why they displaying 25 only? That means in that whatever the displaying in the glass, no two are same. If the union of all the disjoint will give the whole distinct number of shoes. You never keep the two same model in the glass. So one is represent one class. The union of all that will give the total different kinds of the shop, different kinds of the shoe in that shop. So indirectly what is doing, the means that is not having only the 25 shoes. The model one represents so many are there in the back end, in the godown. So instead of all, you will keep one representing one only, the model one only. Similarly model 2. So the total shoes in the shop is divided into the disjoint union. So one is represent one equivalence class. The union of all will give the whole different kinds of shoe in the shop. No two are equal in that one. So the one is represent one equivalence class. So the concept of equivalence class is nothing but we are dividing the set. So whenever we require the partition, we can use the concept of equivalence class. For example, I will take one relation. I think modulo 3, for example, modulo 3. What is the meaning by modulo 3? So for example, I want to divide the whole natural numbers into 3 groups. So my objective is what? To divide the whole natural numbers into 3 groups by using the concept of equivalence relation. What is the relation I am taking? I am taking the relation addition modulo m, or sometimes it is a addition modulo 3. So what is the meaning of this one? A is nothing but R is the remainder when we divide A plus B by 3, that is the value. So now I am dividing the whole 0 bar, 1 bar, 2 bar. Now look at here, 1 bar is the one equivalence class, 0 bar one equivalence class, 1 bar is another one, 2 bar. If you take it, any number will come under either of this group. How it will, for example, 0 bar, all the multiples of 3 I am keeping in this one, like this. Why I am keeping this one? By using the relation addition modulo 3, when we divide by 3, leave the remainder 0, or will come under the category 0 bar. 0 bar is one equivalence class. Which equivalence class? Whenever we dividing by 3, leaves the remainder 0. In the similar manner, 1 bar. What is the 1 bar? 1 bar is the equivalence class, will leave the remainder 1. When we divided by 3, what elements will come? Plus or minus 4. Like that elements will come. Similarly, 2 bar. All the elements when we divided by 3, leave the remainder 2. So therefore, the set of whole numbers I divided into only 3 groups by the defining the relation only. What relation? Addition modulo 3. This relation is equivalence relation. So this equivalence relation divide the whole into disjoint sets. So here 1 is represent one equivalence class. Here 0 bar is one equivalence class, 1 bar is one equivalence class, 2 bar is one equivalence class. If any number is there, either come to the any one of this group. No two are common. So the whole set I divided into 3 disjoint equivalence classes. So the purpose of defining equivalence class is to segregate the given set, to partition. So whenever the moment you require partition of a set, so we can use the concept of equivalence class. Okay, hope you clear this equivalence class, but we are in the process of defining the function. Now we define the relation. Now then once we define the relation, we can define the function. Suppose f a to b is said to be function, if first there is a relation from a to b. After that, what is the condition? Every element of a assigns unique element of b. Every element of a assign unique element of b, then that relation is called function. So for defining the function, we need relation. After that relation, what are the rule? For here a is called domain and b is called codomain. In order to become that relation is a function, so you must have every element of mapping and associate with unique element of b. Then that relation is called function. Now let us discuss one example. Okay, for example, I will take a is equal to 1 comma 2 set having 2 elements, cardinality is 2, and b I am taking elements a, b, c, the cardinality is 3. Now we will construct a cross b, and we know what are the how many members will come in a cross b? Number of elements of a into number of elements of b. So a having 2 elements, b having 3 elements. So a cross b having 2 into 3, 6 elements. So we know the definition. This is the 1a, 1b, 1c, 2a, 2b, 2c. So this is a cross b. But now I will take, we know the what is the relation. I will define 3 relations. Now let us say R1. R1 is equal to 1a and 2b. R2 I am taking 1a, 1c and 2b. R3 is 1a. Now clearly this R1, R2, R3 subset of A cross B. So clearly this R1 is subset of A cross B. Similarly R2 also subset of A cross B. R3 also subset of A cross B. What is the subset? So every element of R1 is element of A cross B. Therefore subset. So after now it is a relation from A to B. R1 is a relation from A. Then how to make it function? Now the question is this R1, R2, R3 are function or not? So better for understanding, I will represent in Venn diagrams so that we can easily visualize. This is a 1, 2, A, B, C, 1, 2, A, B, C, 1, 2, A, B, C. Now first we will draw this R1 in Venn diagram, 1A, this is 1A, this is the map, okay, 2B, this is R1. The similar manner I will represent R2 also, 1A, 1C, 2B, okay, this is R2, then 1A, Now, which are the relations are function now? Now, I define the function. What is the function? F A to B is said to be a function. First, there is a relation. After that, every element of A, the unique element of B. Just look at this one, whether it is satisfying or not. What are the elements we have? A, 1, 2. So, every 1 and 2 having the mapping, look at that one. Yes, 1 is also mapping and 2. Therefore, it is a function. But look at the second one. R2 is a function. Look at which is the fails. Yeah, every element have mapping, but it fails the condition, uniqueness. Look at 1 is mapping to A, 1 is mapping to C. We have to map unique element. Every element of A assign unique element of B. So it is a contradiction to the function. So why? Because 1 is mapping to A and 1 is mapping to C. So this is not a function. This relation is not a function. But look at this relation. Whether it is a function? No. What is the condition? This one. Every element of A domain should have map with the elements of B. But there is no map for 2. So because of that reason, it is not a function. It is not a function. So same thing, now clear, every function is a relation. Every function is a relation, but every relation is need not be a function. Just look at R2 and R3. Relation but not a function. Similarly, we can visualize with graphical also how it is look like. Okay. So I will take the first one is this one. This is R3 I will take. Okay. Yeah. We'll take the points. This is the 1, 2, sorry, AB, 1, 2, 3. In x-axis I am taking AB and y-axis I am taking, x-axis I am taking 1, 2 and y-axis I am taking ABC. Okay, like this is 1, 2, A, B, C, 1, 2, A, B, C. Similarly, this is 1, 2, A, B, C. This is another way of representing. Same thing. I will graphical. I am representing this relation. Now we will represent R1 here. What is R1? 1A. Take it. 1A. This one. 1A. 2B. This one. Just join this. This is the graph of this one. So this is the R1. If you represent graphical, this is R1. So look at the second 1A and 1C and 2B. So this is the one, the graph of this one. Okay. But look at 1A. So geometrically we want to visualize what is the function. What is the geometrical? Now I want to explain geometrically what is the concept of function. When it is the graph is function, when it's not function. Just look at this is function, we know. This is not a function. This is not a function. Just look at here. So whenever we have one is mapping to A, one is mapping to C. So whenever one element mapping to more than one element, definitely will get the line parallel to y-axis. So very simple, whenever the line parallel to y-axis, that graph is not a function. Not a function. Okay. And look at here, there is no mapping from the domain element here. Because of that is not a function. So let me clear with some more example this visualization. Yeah. So I will draw some graphs here. Now you identify which graphs are function, which graphs are not a function. We'll start with the first one. All this I think familiar curves. Just look at these graphs and which graphs are functions and which graphs are not function. And most of you have some misconceptions also is there that I want to emphasize this one. all the equation versus function. So most of they will see equation versus functions. Equation versus function. So all equations are function. Just think it. So whatever you write, they are functions. For example, if I write for example y square is equal to 1 minus x square, y square is equal to x, y is equal to x square plus 1. All these are equations, but all these are functions. Just think it. I will clarify after this explanation. Now just look at the first one. Just look at the first one. Is it function? Now I define mathematically what is the function I give it. So just same thing I am interpreting to graphically. So what is the function? First it is mapping from A to B. After that mapping, relation from A to B. After the relation, I satisfy the condition. What is the condition? What is the rule of that one? Every element of domain associated with unique element of codomain, then that relation is called function. Now same thing we can bring into the graph. Okay, just look at this first one. Yes, it is a function. If you take any element, generally we will take domains in the x-axis, the codomain element in the y-axis. This is familiar, everyone knows that. Now this is the graph. If you take any element, you have the unique element of B. So it is a function. But this is not a function. Why it is not a function? It is a line parallel to y-axis. Means why it is not a function? The one element you are mapping to more than one element. So here this one is mapping to so many elements. So this is the contradiction to the function. What is the function? Every element of A, also unique element of B. This is the failure of uniqueness. Therefore, it is not a function. So how to remember that one? Any line parallel to y-axis is not a function. Very simple. Now look at it is a function. But look at this one. Look at this one. So look at here one. If you take it like this one, this element mapping to this one and this one. The one element is mapping to is a parabola symmetric on x-axis. It is not a function. Again fails the uniqueness. This member is mapping to here. This member is mapping to here. Therefore, it is also not a function. It is also not a function. But look at this one. Circle equation is a function? No. Clearly, look at this one. This is mapping to here. This is mapping to here. It is also not a function. But it is a function. It is not a function. It is a function. So what we conclude from graphically, if any line generally parallel to y-axis, it is not a function. Or any curve intersect more than one's y-axis is not a function. Look at this curve. Here intersect, therefore not a function. That is the failed uniqueness. So if you remember this one, so we can easily, whatever the diagram if you draw, we can tell that whether the graph is function or not. This graph is, therefore it is not a function. In the similar manner, all equations are not function. All equations are not a function. This is a function, but this is not a function. Why? Why it is not a function? Put x is equal to 1. Put x is equal to 1, then what you will get? Y is equal to plus or minus 1. So 1 is mapping to 1, 1 is mapping to minus 1, which is contradiction to the mapping function. Similarly, this is the y square is equal to x, this graph. Now this is the circle equation. Here put x is equal to 0, put x is equal to 0, what you will get? Y is equal to plus or minus 1. Therefore, 0 is mapping to 1, 0 is mapping to minus 1, again which is the contradiction. Therefore, all equations are not a function. Not a function. So, hope it is clear. So, geometrical and also you can remember the 2 points, the takeaways to geometric interpretation. If any line parallel to y-axis, it is not a function. Any curve intersect more than one's y-axis is not a function. So generally remaining case are symmetrical about x-axis also not a function. For example, if symmetrical about x-axis means, suppose if you draw not only like this graph, if I draw this one, it is also not a function. Why? Because this is the contradiction we'll get the contradiction. Okay, and what is the advantage of this one? Okay, so this I covered in the next video, that one. So hope in this lectures I covered mainly what is the connections with real life, where do we have connection of the function in the real life. Just I started with two three example with motivation. So we define the function mathematically. For defining the function we need relation. First we define the relation, after that we will define the function mathematically. So I gave two three examples, and also after that how to visualize the function geometrically. What is the geometric interpretation of the function? So I cleared this clear. Hope it is clear for the function when given equation is function or not. Given equation is function or not. If I, so for example, if I write a some more example, if you tell it whether it is function or not. For example, if I write here, suppose f of x is equal to, I will write 2 minus x, 0 less than or equal to x less than or equal to 1, and 3 1 less than or equal to x less than or equal to 4. Okay. Similar way, instead of this, if I define this one, if I change, this is a, now is it function? Just look at this one. If I write something equation, all equations are, I already mentioned, all equations are not a function. We have certain rules how to check it is a function or not. Just look at here, put 1 here, 1 is also included here and here. From this 1, so what you will get? 1 is mapping to 1 is mapping to 1. Okay, from this. Here also 1 is mapping to what? 3. Again it is a contradiction. The one element is mapping to two different elements. You have to unique element you have to map, so it is not a function. Then how to make it function, this one? In order to make it this one function, we have to redefine this one. Suppose if we take it as x or 1, then it is a function. Okay. Hope you understand what is the concept of function, how to define mathematically, and how to visualize the function, and how to check it whether the given graphs are functions or not. Okay. Thank you. I am signing off.